Hello everyone, my name is Zhang Kechi. Today I will share our work, learning to represent programs with heterogeneous graphs. The first part is the introduction. Code representation learning aims to transform programs of different formats, including token sequences, abstract syntax trees, or dependency graphs, into vectorized representations. Existing graph-based techniques mostly neglect the semantic type information and adopt the homogeneous graph, resulting in possible ambiguous semantics of the graph representation. In order to tackle the type missing issue within the existing graph-based models, we bring up the heterogeneity of program graphs and try to use the heterogeneous graph for code representation. Now let's introduce our proposed approach. We propose a heterogeneous graph-based code representation approach, HPG-HGT. Given an input code snippet, we first generate heterogeneous program graph according to the ASDL grammar with our HPG parser. In the step 2, we employ heterogeneous graph transformer to produce a vectorized representation. By applying HGT on our proposed heterogeneous program graph, the encoder is capable to generate accurate and delicate representation for programs. Finally, we feed representations into downstream modules for certain tasks. Let's introduce our model step by step below. The first step is HPG parser. To generate a heterogeneous program graph, we firstly assign the node type and edge type information according to the ASDL grammar to build an AST with its nodes and edges tapped. Then we insert heuristic-based manually crafted edges to build HPG, including next sibling, next token, and the reversed edges. Finally, we split the terminal nodes into multiple parts based on the camel case or the snake case and add them with two schemes, including shared subtoken scheme and independent subtoken scheme. After getting the heterogeneous program graph, we use the heterogeneous graph transformer to process it. It is an attention-based heterogeneous graph neural network as the encoder to generate representations upon the HPG. The HGT encoder takes 2 steps to process HPG and produce the representations: feature initialization and iterative message parsing, with heterogeneous message and heterogeneous mutual attention. In the third step, we employ the downstream modules. Most program processing tasks can be categorized into generation tasks and classification tasks. For generation tasks, we collect representations of the subtoken nodes and incorporate the pointer network. For classification tasks, we apply global attention pooling over representations of all nodes in HPG and employ an MLP classifier to conduct classification. The third part is the experiments. We evaluate our approach on method name prediction for generation tasks and the code classification for classification tasks. Following previous work, we choose Code SearchNet Python and Java Small for method name prediction, Python 800 and Java 250 for code classification. The statistics of all user data size are shown in the table. To evaluate our approach, we aim to answer the following 4 research questions, including generation task, classification task, subtoken scheme, and ablation study. The experimental results of RQ1 are shown in the table. We compare our approach with the current state-of-the-art baselines. Our proposed approach generally outperforms the current state-of-the-art baseline models on Code SearchNet Python and Java Small method name prediction tasks. The experimental results of RQ2 are shown in the table. Our proposed approach, HPG-HGT, outperforms all the tree-based and graph-based baselines upon the 2 code classification datasets. From these experimental results, we can also answer RQ3 for subtoken scheme. Different types of tasks may benefit from different subtoken schemes. The independent scheme may be good for method name prediction, and the shared scheme may benefit code classification. The experimental result on RQ4 is shown in the figure and tables. Ablation demonstrates the usefulness of the heterogeneous tabs in HPG. It also confirms the effectiveness of our design for the manually crafted edges in HPG and the decoding strategy over only the subtoken nodes in HGT. The fourth part is conclusion. We are the first to uncover the tab missing issue within the homogeneous graph for code representation. We are the first to propose leveraging the heterogeneous program graph for code representation. Our proposed HPG is capable to relieve the tab missing issue in the homogeneous graph. Specifically, HPG provides the tab information of the nodes and the edges in AST. We propose a heterogeneous graph-based framework based on the HGT architecture to process HPG. Our extensive experiments certify the effectiveness and the uniformness of our proposed HPG HGT. My report is over. Thank you very much for your attention.